What's up guys, it's me Sir Ernest, and today we're going to continue our solution to problem 2.25 of Griffiths 4th edition. Okay, so as a recap, let's read the problem again. Using equations 2.27 or 2.30, find the potential at a distance z above the center of the charge distribution in figure 2.34. So in this case, we're going to use the second figure, or the second configuration, which is a uniform line charge, the same line charge that we had when we discussed example 2.2. Okay, and in this case we're going to compute also for the electric field using this equation, wherein the electric field is equal to the negative gradient of your potential, and we're going to compare our answers with example, in this case example 2.2. Okay, so this is a line charge, so that means we're going to use equation 2.30 in terms of line charges. Okay, so in this case the potential is equal to 1 over 4 pi epsilon naught times integral of lambda divided by script r dl. Okay, this stems from the fact that the potential is equal to, for a continuous charge distribution, is equal to 1 over 4 pi epsilon naught times integral of dq over script r. In this case, dq will be equal to, it will be in terms of your line charge density. Okay, now if you're going to look at this, let's allow me to redraw this. Okay, this is your points and this is your line. Okay, this is along x, this is your origin. Now dl will be a portion of this wire, so this will be your dl. In this case, this will be dx, because the line is along the x-axis, as shown, as we saw in example 2.2. And from the origin, this line element will be at the position x. Okay, if this is z, this will be script r. Okay, so putting everything together, we now have 1 over 4 pi epsilon naught times the integral of lambda times dl, which is dx, divided by script r, which is z squared plus x squared, then you take the square root. So this is square root of z squared plus x squared. Okay, so you already know how to integrate this. So this will now yield to our equation, to the result lambda over 4 pi epsilon naught, and this will be, this will be from negative L to L. Okay, so this will now be natural logarithm of x plus square root of z squared plus x squared. Then we evaluate from negative L to L. You can just take the integral at your own time. So therefore, the potential will now be equal to, potential along z will now be equal to lambda over 4 pi epsilon naught times ln of L plus square root of z squared plus L squared divided by negative L plus square root of z squared plus L squared. Okay, this is your potential. Okay, now as an exercise, you can verify that the electric field when we take the gradient of the potential, okay, that the electric field will now be equal to, indeed, same as example 2.2, which is equal to 2L lambda over 4 pi epsilon times 1 over z times the square root of z squared plus L squared z hat. Because remember that potential is is only a function of z, so this gradient would be derivative of v with respect to z hat, this gradient. Okay, so when you take this one, you will end up with this solution, this results, which is in agreement to example 2.2. Okay, so you can do the verification by yourself already. Okay, so that's it. That's a simple solution to the second configuration of problem 2.25. And in the next video, we're going to solve the last configuration. Okay, so for now, that's all, and I'll see you guys in the next video. Thank you for watching. Bye bye.